Welcome to the Statics and Strengths review portion of Timbers. This review will include calculating support reactions, drawing shear and moment diagrams, and calculating section properties where A is the area, X tilde and Y tilde are the centroid locations, IX and IY are the moment of inertia, and lastly, SX and SY are the section modulus. Let's make sure that we recognize that there are two types of axes used, X being the strong axis and Y being the weak. When beginning the studies of statics, there are some things to consider regarding dimensions, forces, and degrees of freedom. There are 2 dimensions, 3 degrees of freedom, and that means that there are 3 internal forces. The degrees of freedom are delta X, which is the axial force, and the symbol for that is N. There's delta Y, which is the shear force, and the symbol is V, and there's theta, which is the moment force, and the symbol is M. As we start to look at solving for the shear and moment forces on a beam, we can look at the relationships between them that they carry. Then we make a diagram of each to show their correlation. The shear and moment diagrams have some rules regarding each piece individually. Rule number 1 is that the concentrated forces along a member directly affect the shear diagram, but do not affect the moment diagram. This is shown by the first red arrow pointing to the shear diagram. The second rule is that moments along a member directly affect the moment diagram, but do not affect the shear diagram, and that's shown by the second red arrow pointing to the moment diagram. Note that when comparing the relationships between load, moment, and shear, there are 2 things. The first is that the slope of the shear diagram at any point is equal to the negative value of the distributing loading diagram at that point, and that the change of value in the shear diagram between 2 points is equal to the negative value of the area of the distributed load between those same 2 points. The next thing to note is that the slope of the moment diagram at any point is equal to the value of the shear diagram at that point. And the last thing is that the change of value in the moment diagram between 2 points is equal to the value of the area of the shear diagram between those same 2 points. Let's also note that the shear diagram always starts and ends with values of 0. Next, we will look at the slopes of the shear and moment diagrams. We can tell the slope sign depending on which way it is oriented. Starting with a 0 slope, we can tell by the line being horizontal. The slope is positive if it's upward from the left to the right, like the picture shown, and the slope is negative if it is downward from left to right. One thing that's important to note about the slope of a line in each diagram is its order of magnitude, which we can notate in degrees. In the image, we see that each order increases as it goes down per diagram, from load to shear to moment. Now we are going to start learning exactly how to draw these shear and moment diagrams. Rule number 1 is to start by drawing the free body diagram of the structure and solve for support reactions. The picture to the right is a great depiction of about how basic it should be. Number 2 is to draw the shear diagram using the loaded beam and the load and shear relationships. And number 3 is to draw the moment diagram using the loaded beam with the shear diagram and shear and moment relationships. Now that we have reviewed the shear and moment diagrams, let's move on to learning about the moment of inertia. First, we can learn what the centroid is, and that is the geometric center of an object. This is an important part of the moment of inertia. The moment of inertia can be found by the integral of the second moment of an area. It's used for determining beam shear stress and deflection. For a rectangular section, you can use these equations with B being your base and H being your height. So example, Ix equals BH cubed over 12. The section modulus is used to determine the flexural stresses in a member due to the bending moment. Here we can see that the section modulus can be found by taking the moment of inertia I in the corresponding X or Y direction and dividing that by the corresponding C, which is the distance from the centroid to the edge of the section. Here we see that many times structural members are stressed, which means that there is an applied load on them that may cause them to look like these examples shown. Stress is measured by the amount of force per unit area. There are several types of internal forces that can be applied to a member. These include axial force, shear force, and bending force. Axial is typically in tension or compression and is shown by F sub A. Shear is shown by F sub V, and bending by F sub B. First, let's break down axial stress. Axial stress is measured by the axial force P divided by the cross-sectional area A of the member. Note that the axial stress is the same throughout the entire depth of the section. Next, we will break down shear stress. Here, we take the shear force V times the first moment of the cross-sectional area, Q, and divide by the moment of inertia, I, times the width of the given member, B. Note that for rectangular shapes, the equation is simply F sub B equals 3V over 2A. Lastly, let's tackle bending stress. This equation is based off moment and the section modulus. For this, we divide the moment M all over the moment of inertia I divided by the distance to the centroid C. Remember that the bending stress varies linearly across the depth. Let's begin to look at the procedures for solving stresses. Step 1 is to draw the free body diagram and solve for the support reactions. 2. Draw the shear and moment diagrams. 3. Determine the maximum axial and shear force and moment. 4. Determine the centroid location of the structural section. 5. Determine the distance to the extreme fiber, C. 6. Calculate the area and moment of inertia for the section. And 7. Calculate the axial, shear, and bending stresses. One thing we want to question is why stresses. In Steel 1, we used the LRFD, which was the load and resistance factor design. In timbers, we can use that, but of course we're going to use the ASD, which is the allowable stress design. Service loads are used to calculate stresses, which are compared to maximum allowable stresses to see if that particular structural member is adequate. Our last topic of this statics and strengths review will be the topic of beam deflection. This is the amount a beam deforms under an applied load. Deflection is primarily based off of three things. 1. The support conditions, whether it's a fixed, pinned, or roller end. 2. The span type, whether it's simple, continuous, or cantilevered. And 3. The load type, whether it's concentrated, distributed, or an applied moment. The equations for beam deflections can be found in the AISC manual in tables 322 and 323. Here's an example of one of the cases in table 323 where we could find the maximum deflection of a simple beam that has a uniformly distributed load. That is all for the statics and strengths review portion of timbers.